Welcome to machine learning. So what we are going to do today is to begin with some of the fundamental tools that are required in understanding patterns, which is an essential step towards machine classification. Mostly in the course or the lectures to be recorded, I will talk about supervised learning and a little bit of unsupervised learning. So to begin with, some of the fundamentals which are required in machine learning are the linear algebra fundamentals. Okay, so let's begin. So the idea here today is we talk about two key things from an application point of view. So what I'll do is I'm not going to just talk about linear algebra. In fact, I'm not going to repeat what is already being taught as a linear algebra course, but rather I'll start talking about some of the feature engineering methods that are used in machine learning, namely singular value decomposition and principal component analysis. It will be broken into two parts. So first we will talk about SVD and then introduce PCA as a special case of SVD. Okay, all right. Some of the things that we need are vectors, vector spaces, linear independence, span, basis, eigenvalues, and eigenvectors. Okay, of course there are other things that we require and we will introduce those as and when we encounter some of the things. Okay, so there are some of the important results, and I'm not going to rewrite those, and some of these important results that we use in SVD are related to orthogonal matrices. In an orthogonal matrix, when you have a matrix and you multiply the matrix with its transpose, it gives you back the identity matrix, right? Okay. More importantly, the orthogonal matrices are used to interpret rotation, okay, as well as reflection. Also there are some other properties of orthogonal matrices like and orthogonal vectors, which are a set of orthogonal vectors are linearly independent, and eigenvectors corresponding to real and orthogonal corresponding to real and distinct eigenvalues are orthogonal, and transformations by orthogonal matrices are reflections and rotations. So I'll just write down one thing at a time. Transformations by orthogonal matrices are rotations and reflections. That's number one. Number two is also that any matrix vector product is a linear transformation. Okay. These are some of the results that do not require reiteration, but we would require these results anyway. Okay. So what is SVD? So let's take a break and think about this. Okay. So suppose let me introduce a problem to you, and the problem is this, and it's related to something that I do. Is that let's say I have an information matrix. Okay. All right. So I have some matrix, and with a bunch of rows. Right, okay, and you really don't need to know how many rows are there and a few columns. Okay, now essentially this is not a square matrix to begin with. And the number of rows, which are m, are far greater than the number of columns. So what this is some time back we had some data from Scientometrics database. What is Scientometric database is that we have a lot of journals, okay, a lot of journals that have some measures. Okay, now these measures can be thought of as features, okay, in an m by n dimensional feature space. Now what is a feature? A feature is an attribute value for a particular sample. Okay, like for example, if I am doing some physical statistics analysis of a classroom full of boys and girls, so you can say that the weight of a boy and height of a boy, right, these are the features of a boy, right? Okay, similarly for the girl community. So for a journal there are a bunch of features. I mean, you can have I10, H index, H5 index. I really don't want to explain all of that, but what I can tell you at this point is that all these features represent the characteristics of a particular journal, in the sense how good or bad a journal is. Okay, now these are all scientific journals, peer reviewed, have to be weighted. Now the question is, these days what is happening is, because of the rating agencies, I mean, they come up with a lot of metrics, and scientometrics is a very vibrant field. So we do have a lot of these features and attributes for journals, right? So the question is, somebody tells me, okay, look, this particular matrix, this particular journal, this particular feature is better, that particular feature is worse, this and that. So it's becoming difficult to standardize the quality of a journal by one number. So this was the problem. So the problem statement was this. This is the problem statement, that can we quantify journal quality by one metric? Okay, all right, this is a metric and not really a matrix, so just to have the distinction clear. Okay, so where will this matrix, the next question is, where will this come from? Now obviously, I mean, we don't want to define another metric. So we wanted to use whatever matrix or features we already have with the number of samples, and those are journals. So these are your samples, okay, along the rows, which you think for now as journals, and these guys along the columns are your matrix or features. Okay, so what you have is an information matrix. What do you have? An information matrix with a lot of rows, each row representing a journal, and a few columns and each column representing some sort of a feature of that metric. Okay, and as I said, we really did not want to define another metric or a feature. Okay, all right, so we have to work with the information matrix that is given to us. So what are you going to do? Can we think of, so if I extend this question, can we extract a one-dimensional information metric from the data or the matrix that is given to us? So this was the problem. So where does singular value decomposition come in? Now of course the problem statement clearly told us that don't use any other feature, any other metric. So try to figure out one value. Now what we know is, if I recall the principles of linear algebra, we know that if I give you a matrix, of course that matrix has to be a square matrix, and you can compute the eigenvalues of that matrix, right? We know that. Okay, now the problem here is the matrix here is not a square matrix, because as I already told you, I mean, the number of rows are way larger than the number of columns. So since you cannot compute the eigenvalues, can we compute something else? And based on that something else, that if we are able to compute, can you relate back to the information matrix given to us and figure out, based on those values, if we sort them in a descending order, based on those values, whether we can club journals. So the extension of the problem, the equivalence of what I have written on the right hand side of the screen, is that can we summarize concepts from data. And this, by this what I mean is, can we have a band of values, let's say sigma 1, sigma 2, all the way up to sigma n, right, which will correspond to an individual journal. Okay, all right. So this is the problem. Okay, this is the problem statement. All right. Now what will happen is, so in general, what will happen is, I have a matrix A, and this is the matrix which we are calling it as the information matrix. Okay, I have a matrix A, and can I decompose this into, can I decompose this into pieces to gain some insight? Okay, all right. So this is what SVD is. All right, or at least the motivation of singular value decomposition is. By the way, these guys are, as we will find soon, these guys are known as singular values. Okay, all right. Okay. Now I need a few things to introduce about orthogonal matrices and orthogonal transformations. Okay, and of course there is there is this concept of similarity, which means, can I figure out whether two vectors are similar to each other, right? And basically what I do is, even in order to do that, I take the inner product of the two vectors. Okay, all right, and this can be written as the norm of x, which is basically the magnitude of x and y, times cosine of the angle between the two. Okay, so in other words, what it means is, I have a vector in this direction. For the first time since I am drawing vectors, I will be using arrows. In all the subsequent lectures, whenever I draw line segments, we will assume that these are vectors. Okay, so I won't be drawing any arrows. All right, and this is the angle between the two vectors, theta. Okay, now the question is, if I want to know, how these two guys are related to each other, okay, or right, how similar these two guys are to each other, I can simply compute the angle between the two, right? And if the angle is smaller, I can say that these two vectors are sort of aligned in the same direction, or in other words, they are sort of similar. However, if the angles are large and for example 90 degrees, then I can say that x and y are orthogonal to each other, which means there is little similarity between the two. Okay, so if I give you two sets of data, right, and I tell you, can you tell me whether there is instead of there is one way of finding out the similarity or dissimilarity is to compute the Euclidean distance between the two, right? Another way is to look at the inner product. Okay, so that's one thing. We would be generously using inner products, because the next thing that we are going to talk about are the orthogonal transformations. Because what we claim is that orthogonal transformations are angle preserving, and the only way to know that, or one of the ways to know that, is to figure out the inner product or the dot product between the two. Okay, all right, so here is the deal. I have a matrix, I have a vector u in this direction, I have a vector v in this direction. And you know, by virtue of a linear transformation, I can do this, right? I mean, I can have a linear transformation capital T, and if I apply that linear transformation, think of it as a function. So T applies on the U, right? And it produces something like Tu, and T applied on V, it produces something like TV. So if I'm saying that orthogonal transformations are angle preserving, what I'm typically saying is that the angle here, theta, and the angle between the transformed vectors, theta t, are going to be the same. This is what I'm saying, or this is what I'm claiming. Okay, all right. Now, we know from the formula that we have put up there is that cosine of theta is nothing but the inner product of u and v divided by the magnitude of u times the magnitude of v, correct? And this is as far as the angle between the two vectors u and v are concerned. Now let's look at the transform space, right? In the transform space, what happens is the cosine of theta t, where theta t is the angle between the transform vectors tu and tv, you are looking at the inner product of tu and tv and the magnitude of both of this. Okay, all right. What we need to do is that we need to show that these two guys are the same. Okay, all right. Now, can we? I mean, in what way? I mean, see, the only way to show that is that this guy, the inner product of tu and tv, is equivalent to the inner product of u and v, and the norm of tu is equal to the norm of u. That's it, right? Okay. But what do we know about these t guys? We know that this is orthogonal, right? Okay. So which means, for example, I mean, I should not have used t, I should have used something else, but anyway. So let's, for a moment, let's call this t dash. Okay. So t dash, t dash, t dash, t dash here, t dash and t dash. Okay. So let's take a look at the inner product of t dash u and t dash of v. Okay. Now, according to the rule of inner product, what I can do is I can have a t dash transpose t dash u comma v. This is a standard rule of inner product. You must have seen this in linear algebra already. What do I know about this though? Look, I said that t dash is orthogonal, right? So the t dash transpose t dash, okay, has to be an identity matrix. Okay, all right. So I can replace this with an identity matrix, and therefore I have this, and you know this is really trivial, and I get back to u and v. This is something that we claimed, right? Okay. And also it is very easy to see, if I replace this v guy with u, then what I'm doing is I'm taking the inner product of t dash u with itself. If I do that according to the same principle, I will have to replace the v with u, right? Okay. Now we know that the inner product of u with itself is nothing but the norm of u, right? And this is nothing but the norm of t prime of u. So therefore I establish two things. One is that the magnitude of u is equal to the magnitude of its transformed transformation, as well as the angle between the two are the same. Okay. So this is a very, very important information that we use, and therefore we establish the fact that orthogonal transformations are angle preserving. Okay, good. Now back to SVD. So what we want to do is, at least from the point of view of, as I said, if I go back, I have an information matrix which is non-square, and what I intend to do is I intend to decompose it into three pieces, as I said earlier, right? So on the leftmost side you have a matrix, on the rightmost side you have another matrix, however with a transpose, okay, and in between these two matrices you have actually a square matrix. So the interesting thing that you observe here is, on the left is a non-square matrix, on the right hand side out of the 3 matrices 2 are non-square matrices, but the middle one is the square matrices. This is good, right? Because typically speaking, if that's what that means is I am in a position to compute the eigenvalues of this matrix. I mean, if I want, I cannot compute the eigenvalues of A, but I can compute the eigenvalues of the sigma matrix, right? Okay, all right. Okay, moving on, we need a little flashback from linear algebra. We know that in this case for a square matrix, though, for a square matrix, A, this time I am considering A to be a square matrix, okay. I can write A as P D P inverse, okay, and this is known as a similarity transformation. You must have seen this, right? One of the advantages of doing this, and this D is a diagonal matrix which contains all the eigenvalues of A, and P contains the columns of P contains the eigenvectors of A, right? And therefore, if the eigenvalues are real and distinct, this particular matrix P, the columns will be linearly independent, and if the columns are linearly independent, the matrix is invertible, and therefore the inverse on the right hand side exists, okay. All right. One of the advantage of doing this is that, you know, if you know that you can dissolve your matrix in this fashion, it's a piece of cake to actually compute any power of the matrix as you want. For a quick recap, this is nothing but this guy multiplied with itself k times, right? And it's easy to see if you do that, right, you will have a PDP inverse, then PDP inverse, how many times? K times. Now what will happen is, except for the P on the leftmost side and the P inverse on the rightmost side, right, all the intermediate P and P inverses will, you know, yield you identity matrices, right? And what else will have? You will have a bunch of diagonal matrices. How many times? K times. So basically what you are able to write is that this is a P and there is a D to raise to the power of K times P inverse. So this is far simple in terms of computing, right? Rather than, you know, take the, multiply the matrix with itself K times. Okay. So the idea is every matrix A factors into 2 pieces. So every matrix A factors into 3 pieces, and this is the general representation. Now this is the representation that we are going to use in SVD, where this guy U is orthogonal, this guy V is orthogonal, okay, all right, and the guy in the middle, the matrix, is a diagonal matrix. Okay, so where did this come from? The whole idea, if I have to think about it, is there's an intuitive understanding that comes from, eigenvalues and eigenvectors, which amount to stretching. I take a vector, right? Okay, and a matrix vector product, right? So you take a vector and you multiply that with a matrix. So the matrix is equivalent to a linear transformation, right? So what does a linear transformation do? What is it supposed to do? When you apply a linear transformation on a vector, it's going to, map it to some other space, right? So it amounts to some sort of a stretching of that vector. Now, while you stretch it, you may rotate it, you may reflect it, you may push it to some other direction, right? However, if you stretch it in such a way that the resultant of your stretching doesn't fall off the span of the vector, then you create something unique, okay? And this is what we call as So on the left hand side, what you see is that there is some transformation. You have some transformation applied to the vector, right? What do you see on the right? On the right you see the same vector, but the thing is, I mean, you see that vector multiplied by some scalar. So this guy over here is a scalar, right? It's a scalar multiple of that same vector. So what are you doing? If that scalar multiple is large, let's say it's larger than 1. So what happens is it's like this pen, right? I mean, you stretch it as much you want. You stretch it. If it's larger than 1, you're multiplying this guy by a multiplication factor greater than 1. Okay, so it will be stretched. If the value of lambda or the scalar is between 0 and 1, what will happen is it will shrink. Okay, but what you are doing is you apply the transformation onto the vector. You are not pushing it off. You are actually keeping the same alignment, which means this is the span, right? I mean, this is the span, and in that span you are, you know, translating the vector in some in a larger fashion or in a smaller fashion. That's what it is. Okay, so that's the famous eigenvalue eigenvector equation, right? We need to come back to this in a moment, but this is the founding principle. So we will so let's ask some questions here, okay, before we get into SVD. So let's ask some questions. So the question is, what's the difference what is the difference between when you have a square matrix A and you decompose it into this fashion, and you have a non-square matrix A and when you are decomposing into this fashion? What's the difference? Okay, so in other words, I mean, what this guy has bunch of rows, and this guy has bunch of columns, right? Okay, all right, and what this guy looks like is, I mean, if it's, let's say, 2 by 2, you have a sigma 1, you have a sigma 2 here, you have a 0 here, you have a 0 here. Okay, all right, and we conclude this lecture by saying that let's imagine P is orthogonal. If P is orthogonal, then what we know is P inverse is nothing but P transpose, right? So therefore, what we see here is you can rewrite the first relation in the following fashion: PD P transpose. So that way you sort of try to establish some sort of a link between these two different kinds of decompositions. Plus, please understand, but they are still not the same. Okay. So I think we'll probably stop at this point.